Well, how do the Euler solutions look? Well, I'll just sketch. I think from this you can see already, when you start out on the Euler solution, it's going to go like that. Now you're too low. Well, let's suppose after that the line element here is approximately the same as what it is there. You know, roughly parallel. After all, they're not too far apart. And the direction field is continuous. That is, the directions don't change drastically from one point to another. Well, then it'll sort of, but now you see it's still too low. It's even lower as it pathetically tries to follow. It's losing territory, and that's basically because the curve is convex. Exactly the opposite would happen if the curve were concave, if the solution curve were concave. Now it's too high, and it's not going to be able to correct that as long as the solution curve stays concave. Well, that's probably too optimistic. It's probably more like this. So in other words, in this case, if the curve is convex, the Euler is going to be too high. Too low. Let's put E for Euler. How about that? Euler is too low. If it's concave, then Euler is too high. Okay, that's great. There's just one little problem left. Namely, if we don't have a formula for the solution, and we don't have a computer that's busy drawing the picture for us, in which case we wouldn't need any of this anyway, how are we supposed to tell if it's convex or concave? Back to calculus. Calculus to the rescue. When is a curve convex? A curve is convex if its second derivative is positive, because the first to be convex means the first derivative is increasing all the time, and therefore the second derivative, which is the derivative of the first derivative, should be positive. Just the opposite here. The curve, the slope is, the first derivative is decreasing all the time, and therefore the second derivative is negative. So all we have to do is decide what the first and what the derivative, the second derivative of this solution is. We should probably call it a solution. To y of x is a little too vague. y1 means the solution that started at this point. So in fact, probably it would have been better from the beginning to call that y1, except there's no room. y1, let's say. That means the solution which started out at the point 0, 1. So I'm still talking about a solution like that. All right. So I want to know if this is positive, the second derivative is positive at the starting point 0, or it's negative. Now, again, how do you calculate the second derivative if you don't know what the solution is explicitly? And the answer is you can do it from the differential equation itself. How do I do that? Well, easy. Y prime equals x squared minus y squared. Okay, that tells me how to calculate y prime if I know the value of x and y, in other words, the point 0, 1. What would be the value of y double prime? Well, differentiate the equation. It's 2x minus 2y y prime. Don't forget to use the chain rule. So, if I want to calculate at 0, 1, in other words, if my starting point is that curve convex or concave, well, let's calculate y of 0 equals 1. Okay, what's y prime of 0? Well, I don't have to repeat that calculation. Using this, I already calculated that it was negative 1. And now the new thing is, what's y double prime of 0? Well, it is this. It is, I'll write it out. It's 2 times 0 minus 2 times negative y, which is 1, 2 times 1 times y prime, which is negative 1. You want to see we're pulling ourselves up our own bootstraps, which is impossible, but it is not impossible because we're doing it. So what's the answer? 0 here, 2. I've calculated without having the foggiest idea of what the solution is or how it looks. I've calculated that its second derivative at the starting point is 2. Therefore, my solution is convex. at the starting point, and therefore this Euler approximation, if I don't carry it out too far, will be too low. So it's convex, Euler, too low. Now you could argue, well, what about this? You know, suppose it, you know, yeah, you know, so you go like this, and but then it, see, it catches up, and then so, well, of course, if the curve changes from convex to concave, then it's really impossible to make any prediction at all. That's a difficulty. So all this analysis is only if you stay very nearby. However, I wanted to show you, the main purpose of it in my mind was to show you how to use it's these equations, how to use the differential equation itself to get information about the solutions without actually being able to calculate the solutions. Now, so that's the method, and that's how to find out something about it. And now what I'd like to talk about is errors. How do I handle, right. So, I mean, that's in a sense, I've started the error analysis. In other words, the error, by definition, the error is this difference, E. The error between. So in other words, I'm asking here, is the error positive? As it would be, it depends which way you measure it. Usually you take this minus that. So here the error would be considered positive, and here it would be considered negative, although I'm sure there's a book somewhere in the world which does the opposite. Most hedge by just using the absolute value of the error, plus a statement that the method is producing answers which are too low or too high. The question then is, naturally, this is not the world's best method. It's not as bad as it seems. It's not the world's best method because that convexity and concavity means that you're automatically introducing a systematic error. If you can predict which way the error is going to be by just knowing whether the curve is convex or concave, then it's not what you want. I mean, you want to at least have a chance of getting the right answer, whereas this is telling you you're definitely going to get the wrong answer. All it tells you is, and it's telling you because your answer is going to be too high or too low. We'd like a better chance of getting the right answer. Now, so the question is, how do you get a better method? Searches for a better method. Now, the first method which will occur, I'm sure, to anyone who looks at that picture is, look, if you want this yellow line to follow the white one, the white solution more accurately, for heaven's sake, don't take such big steps. Take small steps, and then it will follow better. All right, let's draw a picture. Excuse me. My little box of treasures here. Take anywhere away.